Ya, Assalamualaikum warahmatullahi wabarakatuh dan selamat sejahtera semua bertemu kembali. Okay, now we see one more differential form in momentum equation. Okay, in this formula we consider in x direction. So total force in x direction, for example, so equal d over dt, integration of control volume cv, rho is density times v, velocity in x direction, c times dv, v is volume. Okay, and plus integration of control surface rho v vx in x direction velocity times v dA area. Okay, so this v and a area is normal, so you get a q. Okay, so q times rho, you get m dot mass flow rate, m dot times v, so you get force or momentum. And then these three equation or three formula, okay, we call Navier-stokes equation or NS equation. Okay, first in x direction, so rho d capital D, okay, u dt is a pressure, velocity difference. Velocity, okay, velocity difference. So this is time, times difference. Equal minus dp over dx. P is pressure, so dp over dx is called pressure drop, plus rho gx. Okay, so g is a force due to the gravity, and then a plus mu, this is a viscosity, so force due to the viscosity, so times del squared u over del x squared plus del squared u over del y squared plus del squared u over del z squared. Okay, this is in x direction, and the second in y direction also same. Okay, so only in y, so y direction, and then the third in z direction. Okay, and then we can write for simple. Okay, these three equation we can write in vector. Okay, vector form. So rho dv over dt, v is a velocity vector, okay, for u, v, and w. Okay, and then the pressure drop, okay, minus del operator, okay, p pressure, and then plus rho g plus mu, so del operator squared v, v is a velocity vector. Okay, then v, this we call del operator. Okay, del operator, okay, represent, okay, for example, del squared over del x squared plus del squared over del y squared plus del squared over del z squared. Okay, and then example, okay, we see one example for Navier-stokes equation or momentum equation. Okay, we consider, okay, two plates, at left side fixed plate and then right side is a moving plate with velocity capital U. Okay, is set, for example, so x direction upward, okay, positive, and then y direction, okay, then distance between two plates delta, so g, say downward, for positive g gravity. Okay, for this okay problem, okay, to determine the velocity distribution between the plates means u, small u over capital U. Okay, velocity difference. Okay, okay, first assumption. Okay, in this case we can assume pressure is constant. That means no pressure difference or pressure drop. Okay, so P constant. And the second, flow is steady, steady flow. So del u or du over dt, okay, equal dv over dt equal 0. Okay, in velocity not change, respect to time. And then third, flow is fully developed. Okay, means, okay, from initial to the end, so the velocity profile is same. Okay, so we call fully developed. Flow is fully developed in x direction. So del u over del x equal 0. Okay, and then del, okay, over del x times del u over del x equal 0, because del u over del x equals 0. Okay, and then third, okay, for boundary condition, okay, first, okay, y equals 0, u, small u equals 0. Okay, That means y equals 0 at this fixed plate. Okay, so y equals 0, so u equals 0, because this is a viscosity due to viscosity, so due to no slip condition, so u equals 0. And then the second boundary condition, y equal delta. That means y equal moving plate, so y equal delta, so u, small u equal capital U. Okay. Then v velocity v also y equals 0, so v also equals 0, and then v here, so y equal delta, so v also equal 0. Okay, no velocity in y direction. Okay, and then okay, 5, gravitational acceleration gx. Okay, this is a positive direction, okay, outward, so gravity downward, so negative g. Okay, so negative g. Okay, how to determine the u over capital U? So first, from continuity equation, okay, you know, okay, two-dimensional Cartesian coordinate, so del u over del x plus del v over del y equals 0. So you apply, okay, del u over del x equals 0. Okay, so you get del v over del y equals 0. Okay, and then second, we apply second Navier-stokes equation, KNS, Navier-stokes equation in x direction. Okay, we take first formula in x direction. So this represent d over dt. So rho du over dt plus rho v del u over del x plus rho v del u over del x equal minus, okay, pressure drop, okay, del p over del x plus, okay, minus rho g, because g is negative. Okay, it's negative. Okay, plus mu. Okay, then okay, all this. Okay, then we substitute del u over del t. Del u over del t equals 0, del u over del x equals 0. Okay, del u over del y. Okay, this is also equals 0. Okay, and then pressure drop also equals 0, no pressure drop, and then you can get okay, here, okay, del square u over del y squared times mu, so equal rho g. Okay, and then this is a partial derivative, so for total derivative, so we can write d squared u over dy squared, okay, equal rho g, so over mu. Okay, and then third, integrate and solve for u. Okay, integrate first. Okay, first integration du over dy, you get rho g, so rho gy over mu plus constant, okay, c1. And then one more, integrate, so du over dy, you integrate, you get u. Okay, so rho g, so y we integrate respect to y, so y squared over 2 mu plus c1 y plus c2 constant. And then fourth, we substitute in boundary condition. Okay, first, okay, boundary condition, okay, y equals 0, u, small u, equal 0. Okay, at a fixed plate. Okay, we substitute y equals 0. Okay, y equals 0 and u equals 0. Okay, u equals 0, y equals 0. Okay, y equals 0. Okay, we can get constant c2 equal 0. In the second boundary condition, y equal delta. Okay, y equal delta at moving plate. Okay, so u, small u, or local velocity equal u, capital letter U. Okay, substitute. Okay, u here, small u, substitute with u. Okay, then rho g y, okay, square, so y substitute with delta, okay, square over 2g plus c1, okay, c1, so y substitute delta, and then c2 equals 0, okay. Then we get c1 equal u over delta minus rho g delta squared over rho mu delta, okay. So delta cancel, okay. C1 get u over delta minus rho g delta over 2 mu, okay. And then we substitute c1, okay, substitute c1 with this equation, and then get u, okay, u small u equal rho g y squared, rho g y squared over 2 mu plus, okay, c1, okay, c1 substitute with this as this, okay, and then u over delta minus rho g delta over 2 mu, this is y, then c2 equals 0, and then all this we divide by capital U, okay, to get the velocity distribution small u over capital U, okay. So rho g y squared over 2 mu u, okay, plus u over u, okay, so can be cancelled, so this y, okay, times, okay, u, so y over delta, okay, minus rho g delta y, rho g delta y over 2 mu u, okay. And then the last okay, formula equation, you can get u over u, velocity distribution, okay, u small u mean local velocity, so u and maximum velocity, okay, minus y over delta, so delta is a gap, okay, clearance or difference between fixed plate and moving plate, okay. So y, okay, at any point, okay, plus gy squared over 2 nu u, nu is equal, nu equal kinematic viscosity mu over rho, is a rho over mu, so mu over rho equal nu kinematic viscosity, so minus g delta y over 2 nu u, okay. This is we call velocity distribution, okay, between two plates, mean at left side, left plate fixed, and the right side is, or right plate is moving, moving plate. So the velocity profile is this, okay. And then we can get the velocity profile or velocity distribution, just substitute y at any point, okay, and then delta is a constant, so nu constant, u constant, g constant, so y only y, okay. Okay, thank you.